In this chapter, we will talk about long-run economic growth for the first time, and we'll focus on some facts. If you see the graph here, it shows economic growth over the very long run for 6 countries. And adjusting for inflation, we see that the United States and the United Kingdom took off in terms of economic growth sometime around 1800. Of course, that's the period of the Industrial Revolution. The increase in standard of living over the last 200 years has been almost exponential for those 2 countries. Sometime later, Japan followed, and there are countries today who are catching up, although they still have a ways to go. This is quite a remarkable diagram. You notice that over the very long run, per capita GDP was stuck at about $500. And there's a reason for that. If the average per capita GDP fell too low, people could not survive. There had to be a floor, as it were. But that floor tended to be a baseline. It's only in very recent history that there's been significant improvement in the standard of living for the regular person. This question of economic growth was the subject of the famous book by Adam Smith, An Inquiry into the Nature and Causes of the Wealth of Nations, usually called The Wealth of Nations for short. Adam Smith wanted to understand, why did standards of living begin to grow rapidly around the late 1700s, and why did some countries become rich before other countries did? That was the great question, and that was the beginning of what we call economics today, this great book, The Wealth of Nations. This is the statue of Adam Smith in Edinburgh. It's on the High Street, which is the main historic street in Edinburgh. And it's surprising, but this statue was only erected a few years ago. The person who unveiled the Adam Smith statue and gave a dedication was Vernon Smith, who has been a visitor at UAA and is actually has emeritus faculty status at UAA. I just wanted to point out here the linkages. The topic of long-run economic growth links to Adam Smith and the famous book in economics, The Wealth of Nations. Adam Smith links to Vernon Smith, and Vernon Smith links to University of Alaska Anchorage, and you guys. Now, here's an interesting question. Out of all the famous economists and famous people in the world, why on earth did the Scots choose Vernon Smith to unveil a statue? Vernon Smith is an experimental economist. He's not a macroeconomist. He's certainly not Scottish. He grew up on a farm in Kansas during the Great Depression. Well, I can't get into that, but it's quite an interesting story, and perhaps we'll come back to that at the end of the course. Okay, so let's get into the real work now. We are going to begin to lay the foundation for economic models of growth. And economic models use symbols, terms, expressions, and equations, of course, like the little photo from the textbook there. The way we will approach this is a cumulative process where we will introduce terms and symbols and conventions of how symbols look and what they mean, and we will build up toward more complex models beyond simple equations. The good news is everything is consistent in your textbook. So once you learn a certain convention, it stays the same in every chapter. So to give you one little example, if you look at that equation there, the bar over a symbol means that the value of whatever it is stays the same throughout all the working of the model. In other words, the A0 with a bar, the L with a bar, and the G with a bar keep the same value no matter how we play around with the relevant model. We're talking about economic growth in this chapter, so we need to take our first steps toward developing some equations. And the most basic step is, how do we measure economic growth in terms of the models? Well, the way we'll demonstrate it is, imagine a world in which time is divided into discrete periods, indexed by t. So there's like a t equal to 0, a t equal to 1, a t equal to 2. And you can imagine each value for t represents a different year. So when we're measuring economic growth over 1 year, we use small y t plus 1 minus small y t divided by yt. So that's like saying the GDP in year t plus 1, it has subtracted from it GDP in year t. That difference, which hopefully is a positive difference, a positive number, gets divided by yt. And now we have a percentage rate of change from moving from t to t plus 1. You'll notice there are no bars over the y's in this little expression. So there are no fixed values for yt or yt plus 1. Now let's imagine that over time this economy has a constant growth rate, and we'll call that growth rate G with a bar over it. So G bar might be something like 2%. Then an alternative way to write the transition from yt to yt plus 1 is to have yt plus 1 on the left and say that is equal to yt multiplied by 1 plus the rate of growth. So if the rate of growth is 2%, yt plus 1 is always going to be equal to yt times 1 plus 0.02. By the way, is there a significance to using lowercase y instead of uppercase y? Yes, there is. In this textbook, when a variable like y is in lowercase, it means that we have converted it to per capita terms. So capital Y is total output of the entire economy. Lowercase y is per capita output. Let's take another example, but we'll use population growth as the object of our interest. Capital L is the total labor force in the economy. and capital L is also the population of the economy. So that's like saying everybody is employed, nobody is unemployed. The size of the labor force and the size of the population are the same. So let's suppose the population is growing at a constant rate, like 2%, and that constant rate stays the same throughout the entire period of interest. Then small n is the 2%. The bar over the n means that the rate of growth remains fixed at 2%. Now, if the rate of growth of something remains the same, then it's easy to figure out what the future value of a variable will be. So if initially, at the start of history, we start with per capita output of y subscript 0, and we want to know what will per capita output be in year t, all we have to do is set yt equal to y0 multiplied by 1 plus the constant growth rate, lowercase g, and the 1 plus g is raised to the power t. That's the number of time periods you compound the growth rate. You compound the increase in output. Since we're talking about growth rates, let's talk about the rule of 70. The rule of 70 is an approximation method, and it says that if you want to know how long a growth rate of X% will cause a value to double, approximately divide 70 by the number X. So if your country is growing at 10% per year, it will take approximately 70 divided by 10, which equals 7 years, to double in its GDP. And the reason why we like this rule of 70 is not because we need it to help us calculate stuff, but it's a simple way to illustrate a very important fact about long-run growth. This is the very important fact. It is that a small increase in the growth rate can have a profound impact on the standard of living after one generation. Got that? Even a small improvement in your country's growth rate, if it is maintained long enough, will cause a profound improvement in the standard of living. Let me illustrate why what seems like a small increase in the long-run rate of growth has very powerful implications. We'll take a hypothetical example. My country is growing at 4% per year, and your country is growing at 2% per year, and we'll keep that going for 70 years, one generation. Now, when you say it like that, most people will think it is not a big deal. Maybe after 70 years, my country might be twice as rich as yours, let's say. That's the intuition. But the intuition is wrong. If you use the rule of 70, a growth rate of 4% maintained for 70 years will cause GDP to increase by 16 times. But if your income is growing at only 2%, then after 70 years, total income has increased by 4. So that difference of 2%, growing at 4% per year instead of 2% per year, leads to my country being 16 times richer than your country. Small increases in the rate of growth if maintained for 70 years, can cause a country to become much richer than it would otherwise be. Now we need to talk about another concept, which is the ratio scale. And here's the intuition. If when we studied growth rates, we used a vertical axis with an absolute uniform scale, it will be a problem. And the problem is, think of population growth. If you use an evenly spaced vertical scale, normal population growth will look exponential. So partly the problem is that line will tend to go off the chart, off the diagram, if you consider a period of time too long. That's one problem. But another problem is that if you're trying to compare different countries by looking at their exponential rates of growth, it is hard to figure out turning points. It's hard to figure out where differences in growth occur. Comparing different exponentially shaped curves is difficult. Now, a ratio scale is a scale where the vertical axis increases by multiples, like always increasing by a factor of 2, or always increasing by a factor of 10. Now, when you have the vertical axis increasing in that way, it's called a ratio scale. When you do that, and now you look at the lines, the graph lines, what you see is that if growth is at a constant rate, like 2%, then the line will be a straight line. And the advantage of having a ratio scale then is we can look at different rates of growth for different countries, and we can figure out when changes occur. Now, we need an example to make sense of that I just explained. Here's the first example. The left-hand side is when you are not using a ratio scale. You see the vertical axis increases in units of 10. It's a jump, and the distance, the scale is the same for the vertical axis. Look at the graph on the right-hand side. Now we're using a vertical axis where each jump on the vertical axis is a doubling. You go from 0 to 6, 6 to 12, 12 to 24, 24 to 48. Now, with a constant rate of growth, the line on the right-hand side is a straight line. So here is the application of this ratio scale depiction choice to real data over real history. And so what you see here is per capita GDP in 7 different countries, adjusted to constant dollars, 2005 dollars. And we can see how per capita GDP grows at different rates in different countries over time. So it won't surprise you to see that there came a point at which Japan's rate of growth increased. There's that bend upwards, but then Japan's rate of growth fell back to a lower constant level, and you see the kink in the graph for Japan go down. You see that for the United States, the rate of growth over 100 years has been consistently around 2%. That's why the US has a straight line. For China, you can see that there was a big takeoff, a big increase in the rate of growth, and it happened around 1978. 1978 is where the notorious Cultural Revolution ended and China suddenly switched to a more market-based economy. And you can tell stories about the other countries on the graph there. By the way, one small detail. Go all the way to the left, before 1880. Look at the graph for the United Kingdom. The United Kingdom started out with a higher per capita GDP than the United States. That's because the Industrial Revolution started in the United Kingdom before it started in the United States. But eventually the United States caught up a little bit after 1900. Look at Germany. You see that around the end of the First World War, 1918, German growth rate fell drastically. It was no longer increasing at around the same rate as the US, and it wasn't until after World War II in 1946 that the rate of growth of Germany increased again. You see a similar thing with Japan, except that Japan was never badly impacted by World War I. So the point is, using a ratio scale makes it much easier to figure out and interpret the data when it concerns growth rates. Now, the textbook has a section that gets into some of the algebra, some of the simple equation style math to do with rates of growth. And I'm not going to go through all those rules with you. It's in the textbook, and I assume you can catch up for yourself. But basic ideas are like this. If the left-hand side is a value like yt, and the right-hand side is a group of variables or values, and that they're being multiplied together, when you take the percentage rate of change of the left-hand side and the percentage change of the right-hand side, the percentage change of the right-hand side in this example will equal the percentage change in A, percentage change rate of growth in K to the 1/3, plus the percentage rate of change in L to the 2/3. So when you take a percentage rate of growth, three variables multiplied together now become percentage change of rate of growth of the first variable plus percentage rate of growth of the second variable plus percentage rate of growth of the third variable. The final line that you see there takes it one step further. When you take the percentage rate of growth for a variable like k to the 1/3, that is equal to 1/3 times the rate of growth of k or L. The bottom line is, I'm leaving it to you to work through all this and figure it out and be competent in using it, because we will use it in different modeling experiences. By the way, that first equation, y equals a times k to the 1/3 times L to the 2/3, should be familiar to those of you who've done intermediate microeconomics. It's a production function using the Cobb-Douglas type formulation, and what we do here is we're taking the formula for production by a factory or a firm, and we are scaling up the concept to apply to an entire country. So now the A is no longer a technological parameter for a factory or a company, it's a technological factor for a whole country. The K, the capital, is no longer capital for a company or a factory, it's the total capital stock for a whole country. And the L is no longer the labor force for an individual company or factory, it's the total labor force for a whole economy. So that equation is really just scaling up to the national level what we already understand about at the microeconomic level of the individual factory or the individual firm. But more on that later. Now, the very last section of the chapter briefly discusses costs of growth. Doesn't economic growth involve costs like pollution? And indeed it does. And those costs are typically quite serious when a country is working through the early stages of economic growth, the early stages of industrialization. And every country that's gone through that transition has had to work through a period where costs like pollution are serious. But when we look at the data on human health, when we look at the data on lifespan, when we look at the data on infant mortality, it is worth it to go through that intermediate stage to get to a higher standard of living, because people in rich countries live longer, they have fewer kids die in childbirth, they have better access to medical care, and they can afford to take care of their environment and engage with pollution mitigation measures. So, yes, there are costs of growth, but looking at the experience of countries, it is worth it as long as you get there, as long as you get to that developed state. See you in the next chapter.